Now let's use the first derivative test to find the relative min and maximum and the absolute min and maximum values for trig functions. So trig functions oscillate up and down, and so they're going to have probably an infinite number of relative min and maximum values. And so usually when you're given a trig problem, they're going to give you an interval that they're interested in. So this is the sine of 3x, and it's over the interval 0 to pi. And we want to find both the relative and absolute min and maximum values. So for the absolute, this is a continuous function over this interval. So to find the absolute minimum and maximum values, so it'll obtain both the absolute min and maximum values over this interval. And so you find the critical points and then evaluate the function at the critical points as well as the endpoints of the interval. Whichever one is smallest is the absolute min, whichever one is largest is the absolute max. So let's go ahead and find the derivative here. And so this is just cosine of 3x times the derivative of the inside function, which is 3. And so I could rewrite this 3 cosine of x. Cosine of 3x, sorry. Three cosine of 3x. That looks messy. So I'm going to write it again. There we go. So that's the derivative. So now let's set that equal to 0. So we're going to have to remember how to solve trigonometric equations. And I think a lot of these are going to be some of those special angles on the unit circle, and you're going to want to use exact values for problems like that. So for this is a multiple angle, that 3x inside. So what you're going to do is you're going to ask, okay, what angle do you put in here that gives you 0? Okay, and then you're going to set 3x equal to that angle, and then we'll need to find all of the angles between 0 and pi. Okay, so let's see how this is done. So I could divide both sides by 3, so then I'm just asking, when is this equal to 0? So here's my unit circle. So the cosine of x is equal to 0 at pi over 2 and 3 pi over 2. Okay, so what I'm going to do is I'm going to set up an equation, an expression for all of the solutions for each of these. But it'll be 3x is equal to pi over 2 plus k times 2 pi. And 3x is equal to 3 pi over 2 plus k times 2 pi. So I'm using the 3x there. And then I divide both sides by 3. And when I do that, I get pi over 6 plus k times 2 pi over 3. And then this would be x is equal to, this will end up being pi over 2 plus k times 2 pi over 3. Okay, so now k could be, to get all the solutions, you plug in the negative, positive integers here, and then multiply them. It's all these multiples added and subtract, all the multiples of 2 pi over 3 added and subtracted to pi over 6. So any of the negative multiples are going to take you outside this interval. So pi over 6, when k is 0, pi over 6 is one solution. And then when k is equal to 1, you're going to get, this will be 5 pi over 6. And so that's another solution. When k is equal to 2, you're already outside the interval. So that's the only one you would get there. And for this one then, let's see, you would have, when k is 0, you would have pi over 2. But when k is 1, you would be outside the interval. When k is -1, you'd be outside the interval. So these look like your critical points. So what I'm going to do is I'm going to set up my table with that. So 0 to pi over 6. That takes you up to the critical point x is equal to pi over 6. And then I have, looks like my pen is running out, I'll have pi over 6 to pi over 2. That takes you up to the pi over 2 critical point. And then pi over 2 to 5 pi over 6. That takes you up to this critical point. And then you have 5 pi over 6 to pi. Not 2 pi, but up to pi. And so now I need a test point out of each of these intervals. So I can't get a special angle in here, because 0 to pi over 2, it has to be inside there. So I'm going to do pi over 12. But notice when I put pi over 12 into this derivative, I'm multiplying that by 3. And so I'm going to get pi over 4. So that still is going to be, it's going to involve the special angles. Okay. Now this one I can use pi over, let's see, 2 pi over, or pi over 3. I can use that. For this one, I can use 2 pi over 3. And then this one, I'm going to need one of those, the 11 pi over 12. I'm going to need that special one. Okay, so now I need to evaluate this function at each of these. And I've done this already, so you could plug that in. You get pi over 4, and that would give you square root of 2 over 2, and so this would be 3 square root of 2 over 2, and that would make this positive. Okay, so I won't worry about doing that every time, but when I stick in pi over 3, and this is the derivative here, when I stick in pi over 3, this becomes negative 3. And I get a negative derivative. When I stick in 2 pi over 3, this becomes positive 3, and that's a positive. And then when I stick in 11 pi over 12, this becomes negative 3 square root of 2 over 2, and that's negative. So what I see here is this goes from positive to negative, so you got a relative max here. This goes from negative to positive. You got a relative min. From positive to negative, relative max. And so these are the relative min and maxes using the first derivative test. So now, to find the absolute min and maxes, I'm going to plug in each of these points into the original function along with the endpoints. So f at 0, f at pi over 6, f at pi over 2, f at 5 pi over 6, and then f at pi. And then when you plug these into this original function, you end up getting 0 for this, positive 1 for this, negative 1 for this, a positive 1, and then 0. So it looks like you're going to get a max at x equals pi over 6 and 5 pi over 6. And you're going to get a min at x equals pi over 2. Okay, so now we can graph this and just verify that. So sine of 3x, let's see if I can get it here. Oops, and what I want to do is I want to get that over the interval 0 to pi. So 0 to pi. Okay, so you should be able to see it there. So let's try pi over 6. So second calc, if I do pi over 6, let's check. That should be a relative and an absolute max, and it is. So the this min should be pi over 2. Yep, and then the other max should be 5 pi over 6. There we go. So very good. Now this is a problem where I could have probably graphed this, and you know, it would be a period change, but I could have graphed this. This is just a sine wave, and I could have determined those points that way. But this is just illustrating that first derivative test with a fairly simple example using trig functions. So let me do one more here, but one that's maybe a little more involved, and you're going to have to solve a trig equation. We're going to have to use a trig identity to solve a trig equation. It shouldn't be too bad though. So we're going to find the min and maxes for this function over 0 to 2 pi. Now this function, I have no idea what that's going to look like. Okay, so I don't know anything about it, but I'm just going to find the critical points, and then I'll evaluate them at the critical points and the end points like we did before. And I grabbed another pencil here. So let's see. I'm going to take the derivative. So this would be like negative sine of 2x times 2 plus 2 times negative sine of x. So it would look like that. Now I could clean this up to negative 2 sine of 2x minus 2 sine of x. So it would look like that. And now let's set this equal to 0. Now I could pull out a negative 2, and if I do, I would get sine of 2x plus sine of x is equal to 0. And then I could divide both sides by negative 2, and I get this equation. Okay, so how do we solve this? It's not obvious how to solve it. It doesn't seem like I can factor anything out. So this is where an identity is going to be helpful, and I'm going to use the double angle identity for sine of 2x. Can you remember what that was? Sine of 2x is 2 sine x cosine x. And this is perfect because when I replace this with that, I get this, and now I can factor this. I can take a sine x out, and I'm just left with 2 cosine x plus 1 is equal to 0. And now I can set each factor equal to 0, and I got two basic trig equations. Sine x equal to 0, and this would just be cosine x is equal to negative 1/2. And that's perfect. I can solve these. Now, I'm not going to worry about the endpoints. Okay, I'm just interested. The critical points are going to be on the interior. So for this one, it would just be pi, right, when sine is 0. So this will be pi. And for this one, negative 1/2. So if I look at my unit circle, negative 1/2 for cosine would be when the x value is 1/2, and you'd have this one and that one. So this would be 2 pi over 3 and 4 pi over 3. So we'd have those two, 2 pi over 3 and 4 pi over 3. So these are the critical points for this function. So now let's set up a table. So I'm going to go from 0 to 2 pi. To 2 pi over 3. And that takes us up to this critical point. And then I'm going to go from the 2 pi over 3 to pi, that takes me to this critical point. And then I'm going to have pi to 4 pi over 3. So like from here to 2 pi over 3, 2 pi over 3 to pi, pi to 4 pi over 3, and then 4 pi over 3. That takes me to this point. And then 4 pi over 3 to 2 pi. So my table would look something like this. Those are the 3 critical points. And so now let's pick a test value out of each of these. And I think pi over 2 would probably be a good one here. And I have the work done over here. I've done the problem. So if I make this look easy, trust me, it's not. I think this one I had to do twice. Okay, so this is a lot of work. Okay, I'm making it look easy because I don't want you to have to sit and watch me figure it all out, because the videos are long enough without that. Okay, so the next test point I picked here, between here and here, was 5 pi over 6. Okay, and then from here to here I picked 7 pi over 6. And from here to here I picked 3 pi over 2. Was a good test point. So now you have to evaluate the derivative. I would use this cleaned up form. Okay, I'd be careful, don't try to use one of these here, because there can be sign changes here. It's equivalent equations here will give you the same solutions, but you won't necessarily get the same expression when you put something else other than a solution into here. The sign in particular could be different. And so you got to put it back into the original equation here. So the derivative at pi over 2. So when you put it back, and this is tedious, and I would do exact answers, or you don't have to do exact answers. You really just need to know whether it's positive or negative. But when you put it into here, what I got was -2, so it was negative there. So when I put in 5 pi over 6 into here, the exact answer was actually square root of 3 minus 1. And square root of 3 is like 1.6 or whatever, so this was positive. Okay? And then when I put in 7 pi over 6, what I got was 1 minus square root of 3. And so this one was negative. And then when I put in 3 pi over 2, what I got here was positive 2. And so that was positive. So this went from negative to positive, so this was a min. And then it went from positive to negative, so this was a max. And then it went from negative to positive, so this was a min. There was a sign change each time. You had a min, a max, and a min. And so finally, to determine the absolute, and these are the relative min and maxes, to determine the absolute min and max over these intervals, I have to do the original function now at each of the points. Not the derivative, but the original function at each of both the three critical points and the endpoints of the interval. This was okay. So now when you put in each of these, what I got here was 3. And then when I put this in, I got a -3 halves. When I put in pi, I got -1. When I put in 4 pi over 3, I got another -3 halves. And then when I put in pi over 2, I got 3. So there's an absolute max of 3 at x equals 0 and 2 pi, so at the endpoints of the interval. And then absolute min absolute min of -3/2 at x equals 2 pi over 3 and 4 pi over 3. And then this pi here was a relative max, but it was not an absolute max. Okay, it was relative to the surrounding values. So let's check it out here. Maybe I can clean this off a little bit so it doesn't glare. Okay, so now I'm going to put in the original function, and I get cosine of 2x plus 2 cosine of x. Original function, and then I get, let me do my window from 0 to 2 pi. So it comes down. Looks like this. Comes up. So this is what it looks like. And so I'm hoping these relative or absolute mins actually over here are the 2 pi over 3 and 4 pi over 3, which is believable. So let's check and make sure. 2 pi over 3 looks like 1 min, and so 4 pi over 3, there's the other one, and then pi is that relative max. Okay, and then those two endpoints of the interval are the absolute max over the interval. Okay, so there you go. That's using the calculus to tell things about the function. And if we did some thinking, we probably could have graphed this. We would have known that it was a kind of a smooth curve. We would have known that these were mins, and so it had to go from 3 down to here, up to -1, down back to there. And so you probably could have made the graph with the information you got here. And so before graphing calculators, that's oftentimes how functions were graphed. Rather than plotting every point, you can do that, but you can also designate find the min and maximums and connect them up with smooth curves. So, okay, so there you go. You got your work cut out for you. You got to use the first derivative test to find relative min and max and absolute min and max. So good luck with that.